Um, yeah, so today I'm going to present you an experiment in which we asked, is residual vision after optic nerve damage brain state dependent? If you think about, or actually, so what I want to say in the first place is I want to focus a little on the methods because it's, in this case, it's a very interesting experiment which wasn't done like this before, and then but still of course give you a short introduction to the results and then finish with a conclusion. So why is it special? So if you think about visual experiments, people did this for a very long time. They did this until since they actually have these techniques such as MRI or EEG or whatever, and it's as simple as to present subjects with a certain stimulus, like in this case a circle, and then during this they actually record the whatever is going on in the brain. So they had a look at, they usually had a look at what was going on in the brain after you present a stimulus to somebody. But then in recent years they started to actually look at what was going on before the time of stimulus presentation. So here you see some studies on this actually, and yeah, the first two are actually on vision, and they say especially alpha band is very important for some sort of visual attention. And then of course in the last one, which is actually on somatosensory perception, they also say it's not only the frequency bands but it's also connectivity. So why do I say what we did is something that they haven't done before? It's because they have already looked at what's going on in the pre-stimulus state, but they haven't really done it for patients, like for example for patients suffering from vision loss due to damage to the optic nerve. So what would a visual field chart of somebody suffering from damage to the optic nerve look like? This is very simple as this. So in the black field you see they won't see anything, and in the white field they see 100% of the stimuli, but then there is a part in between where they sometimes see something and sometimes don't, and we don't really know why or what is going on here. And so what are these red crosses for? After we did this high resolution perimetry where we get these images from, we actually presented stimuli in these positions. So we had positions in this area of residual vision, which is between the black and the white field, and then one position in the black field and one in the white field. And then after we presented several stimuli in these parts, we only took for each patient these stimuli positions where they had like 50% of hits and 50% of misses of stimuli presented. So they had to press a button once they see the stimulus. Yeah. So why is this different from what people did before? So if you think about the classical threshold experiment, it usually looks like this. So you change, for example, presentation time until you reach a certain presentation time where people hit 50% of the stimuli. But in this case, which makes it different from these threshold experiments, we actually took the damage and then applied a threshold to this. So we only took stimuli positions where they only hit 50% of the targets correctly. Yeah, so I want to give you like a very short introduction of what we found. We found over the occipital cortex that actually in these HIT trials, people had, or actually between the HIT and the miss trials only in patients, we saw a significant difference between in the alpha band. And why do I write patients? So we actually also had controls. How would we have controls with damage to the optic nerve? Well, that works the way that we actually took the blind spot in these. So if you think about the blind spot, It's actually an area where you don't see just due to anatomic reasons. So in these controls, you wouldn't think there would be a difference, because anyway you wouldn't be able to see in the blind spot. So we actually found a difference only in the patients and not in controls, which was very interesting, because it's consistent with what people found before in healthy controls, and it seems like. So if you also have a look at, for example, connectivity measures, and we just started with this, at analyses, it also looks like that things that are important for perceiving the stimulus and pre-stimulus phase are also very important in these HIT trials. So as a conclusion, we can draw that pre-stimulus brain state seems to be very important for people suffering from vision loss in this area of residual vision, because it might be that once you have a malfunctioned input, the brain is actually able to somehow compensate with techniques that are also, or mechanisms that are also found in healthy controls. All in all, what we want to encourage is that people focus more also on the pre-stimulus state, because, as I said, a lot has been done on the post-stimulus brain state, but we're just starting with the pre-stimulus brain state in vision, and I think it's important to also look at the damaged brain. Thank you.